This video has solutions for selected problems from section 9.3 from the book. I selected these problems here, so I thought they were representative of all the things that you need to know how to do. So I skipped problems that I thought were similar, or quite similar to these, and I hope that works for you. So if you understand the solutions to these, you should be fine. And some of these really go beyond what we ultimately need to know about, especially with logistic curves. But we'll talk about that as we get to them. So number 29, we're doing Newton's law of cooling, which says that the temperature of something, the rate of change of the temperature, is directly proportional to, that's the constant of proportionality, the difference between the temperature of the object and the room temperature. So temperature of the room, that's just a constant minus T. The order that you put these things in doesn't really matter. It's going to affect whether your K comes out to be positive or negative. So that decision is kind of arbitrary. In this particular case, in number 29, we're starting with something that where the temperature is of the object, this T is higher. So I'm putting that one here. So I think my K will come out to be positive because this will have the negative in it. So if your answer looks slightly different than this, that's okay. And I might also point out that here, this is a very important skill, I think, to be able to read the text and say, oh, the rate of change is directly proportional to, and then whatever it's directly proportional to. If it's just directly proportional to the temperature, well, that gives us an exponential model, which of course wouldn't make sense for temperature. All right, so A, assume that Newton's law of cooling applies, set up and solve an initial value problem. So we've set up the differential equation, and we know that T, the temperature at time 0, is 95 degrees. So that's our initial value problem. Initial value problem means you have the differential equation, and you have one point, right? One value, which is often the starting point. And now they want us to solve that. Right? So let's see what we can do. We need to separate our variables. I'm going to divide this whole thing over to this side. So 1 over the temperature, I'm just going to call that temperature of room, minus T, d big T is equal to K dt. We integrate. So on this side, this is a constant, this is my variable. So the antiderivative, since this is just T to the first power, and this is just a linear factor of T, it's going to be natural log, absolute value, temperature of room minus temperature, but this has a negative 1 in front of it, so I'd have to divide by negative 1 out here. I'm just going to put a negative sign out here. It's equal to the antiderivative of K with respect to T is KT plus C. Now before I exponentiate, I need to move the negative to the other side. Right, clear that. Anything that's here needs to be cleared out to the other side. I can multiply my C. I haven't solved for C yet, so I can withstand being multiplied by negative 1, and we can still call it plus C. And then I exponentiate. So the temperature of the room minus T is equal to E to the minus KT plus C. And that can come out here as a new C. So the temperature of the room, the temperature of the object, rather, in the room is equal to the temperature of the room minus C e to the negative KT. And my initial value says that at time 0, when this is 0, the temperature is 95. So that means 95 is equal to the temperature of the room, which I also know. What is it, 21? 21 minus, and then C, e to the, when I plug 0 in here, e to the 0 is 1, so that's just C. So my C is equal to negative 74. So that means my solution is T, looking back at this line now, equals the temperature of the room we know is 21 minus C, so that'd be plus 74, because that's a minus there and that's a minus there, e to the negative kt. That gives temperature as a function of time, but notice we still don't know what the k is. So all this is the solution to part A. So put that here. Okay? In part B, how many minutes will it take for the water to reach a temperature of 51 degrees if it cools to 85 degrees in 1 minute? So using the temperature at 85, sorry, the temperature after 1 minute is 85. That gives me another point, which will allow me to solve for k. So plugging those values in, so 85 is equal to 21 plus 74 e to the minus k times 1. And then I can do some algebra here. If I subtract that over here, that gives me 64, and then divide by that over 74 is equal to e to the minus k. I take the natural log of both sides. So the natural log of 64 over 74 is equal to negative k. So k is equal to negative natural log of 64 over 74. So k is 0.145. Nice 3 College Board decimal places. All right, so now I have solved for k. So that means my model now looks like this. 21 plus 74 e to the negative 0.145 t. And they ask me now to figure out if that's true, then how many minutes will it take for the water to reach a temperature of 51? So plugging the 51 in here, and I'll be looking for a time. And then I just need to do some fancy math, pre-calculus kind of math, to solve for t. So subtracting this over here gives me 30, and divide by 74. So 30 over 74. You can reduce that if you want, but no reward really, because we're calculator active. E to the negative 0.145 t. So the natural log of 30 over 74 is equal to negative 0.145 t. So t is equal to that divided by that. So let's see. It's a natural log of 30 over 74 divided by negative 0.145. It's about 6.227. And a time unit here is minutes. Oh, there you go. So it's kind of a lot of work to get through all that, especially if you write out all your steps like I do, which you should. All right, number 33. Here we know that the logistic differential equation looks like this. Just copying this. We've seen this before. K, I like to write ky here so it looks like the exponential differential equation here. They put the y at the back, but I prefer to put it there. Right? That's one way of writing it. And they want to know, they want us to show that the constant functions y equals 0 and y equals L are solutions to the logistic equation. So we'll do y equals 0 first. If y equals 0, then this would become dy dt equals k times y. Well, y is 0, so that's going to be 0, so the whole thing's going to get knocked down to 0. So if the initial condition is 0, then the slope is just constantly 0. So that means we would just have a horizontal line at 0, because it starts at 0 and its slope is just 0 all the time. If the starting condition is L, then dy dt would be equal to k times y, which equals L, times 1 minus y, which is L over L. But L over L is 1, so this is 0. So now anything times 0 is 0, except infinity, of course. So again, if we start out at L, then the slope is just always 0. So that's that. B, explain why the logistic model should behave much like an exponential growth model if y is very small relative to L. We talked about this in class. If y is much smaller than L, then we have dy dt is equal to ky times something that's very nearly equal to 1. Right? That's approximately 1. And if that's approximately 1, then the differential equation is just this, and that's the exponential model. Part C, explain why y increases when y is less than L and y decreases when y is greater than L. Well, because of this factor right here. If y is less than L, then 1 minus y over L. If y is less than L, this is less than 1, so that would be positive. And that means that dy dt would be positive, because everything else is positive. If y is greater than L, then 1 minus y over L. If y is greater than L, this is a fraction that's bigger than 1, so that would be negative, and that would mean the slope would be negative. Again, because that's positive, so this determines the sign. Part D, for what value of y is the rate of change of y with respect to t the greatest? So that's asking for when is the rate of change maximum. In the notes we talked about this, and I think I mentioned it again since then, that the maximum rate of growth happens when y is halfway to the carrying capacity. And we can show that if we want to find the maximum value of the growth rate. That happens when the derivative of this, if you want to find the maximum of anything, you take the derivative of that thing and set it equal to 0. So I'll go through the process here so you can see that again. So the second derivative of this, and I probably should have before I did that. Let me just do it up here. It's going to be a little bit easier to take that derivative if I distribute this. So that's ky minus k over ly squared. Just distributing that through there. And now I'm going to take the derivative. So the derivative of ky is k, right? But y is not the variable on the bottom here, so that means a dy dt pops out, like implicit differentiation. And same thing here. Derivative of this is minus 2k over ly times dy dt. now attempting to clean that up some, we can factor out the dy dt. So that gives me dy dt times k minus 2k over L y, and dy dt is this, right? So if we want this to be equal to 0, it's all in nice factored form here. I've got this factor, and what we know is the rate of growth happens somewhere in between 0 and L, right, as it grows. So this right here is not going to be equal to 0. If you start y out at equal to 0, then you just get a horizontal line at 0. This is also not going to be equal to 0. The only time this is 0 is if you're either at 0 or at the carrying capacity. And actually when you're at 0, this is equal to 1. So we're not going to be at the carrying capacity. So this factor is not equal to 0. That can't be equal to 0. It must be this factor that's equal to 0. So it must be k minus 2k over L times y equals 0. So solving that for y, we get y is equal to, move that term to the other side, and then divide by L over 2k. So it's k times L over 2k. K's cancel out, and there you go. The maximum growth rate happens halfway to the carrying capacity when y is equal to L over 2. Let's see, what are we doing next? 35. So in 35, they're talking about using a graphing utility here, and I should have been more clear with the directions here, that what I'm interested in is you just being able to make a sketch of these things. So, by hand, just based on your knowledge of logistic curves. So let's say here's a graph of y versus t, and here's L, there's our carrying capacity. And I'm going to just make all these sketches here on the same graph, and I'll just label them A through D. So what happens if your starting condition, y sub 0, is bigger than L? Well, in that case, the slope starts out negative, and it approaches the carrying capacity there. So that's what A looks like. And I've shown you the slope field for this too, so the slope field also backs that up. What happens if you start y sub 0 at the carrying capacity? If it's equal to L, then it's just a horizontal line at the carrying capacity. What happens in part C if y sub 0, if it starts somewhere in between L over 2 and L? Well, if it starts somewhere in between there, it's going to look like that. The important feature of that is to recognize that the inflection point happens here, so it will already have turned concave down, right? It doesn't go like that. It doesn't make its S shape here. It's already past the little turn in the S, because we're already past L over 2. And then finally, what if it starts down here? If it starts down here, somewhere in between 0 and L over 2, then it's still concave up until we get to L over 2. That's where the inflection point would be. In other words, that's where the maximum rate of growth is happening. That's what D would look like. So there they are, all rushing toward that carrying capacity. Next one, number 40. So in this problem, they give us the actual solution, a solved logistic equation that looks like this. So you can actually put that in your calculator and graph it if you wanted to. You have to be careful how you set the window. And they also gave us earlier in problem number 34 that the solution for a logistic differential equation, one of the ways of writing it is this. And this is the way that they have chosen to do it here. And I'm going to use this model to figure out what's going on here. So we're going to play a little sort of matching up game here to try to figure out what's going on. So part A, they want to know what is the population at time 0? Well, that's y sub 0. So matching up these two equations, y sub 0 is 1. B, what's the carrying capacity? Well, on the top, we can see whatever number shows up here, 1,000, that's equal to y sub 0 times the carrying capacity. But y sub 0 is 1. We already figured that out, right? So that means the carrying capacity is 1,000. Part C, what's the constant k? Well, there it is, right? K is equal to 0.9. And part D, when does the population reach 75% of the carrying capacity? Well, 75% of the carrying capacity would be 750. So they're basically asking us to solve this equation here for T. So let's go ahead and do that. I'm going to cross multiply here. I'm going to multiply that up to this side. 1 plus 999 e to the negative 0.9t is equal to 1,000 over 750. That's 4/3. You don't have to do that necessarily. And then subtract the 1 over. That would give me 1/3 there, and then divide by 999. So that's 1/3 divided by 999. Right, just consolidating a couple of steps there. And then taking the natural log of both sides, negative 0.9t would be equal to the natural log of 1 over 3 times 999. And so t would be equal to this divided by negative 0.9. I think there's a fair chance that there's going to be some calculator work on this upcoming quiz, right? So there's that, divided by negative 0.9, that's 8.895. Right. And did they give units? They didn't. So 8.895 units of time, whatever those units are. And then part E, they want us to write the initial value problem that would result in this solution. So, well, a logistic initial value problem starts with the logistic differential equation, ky times 1 minus y over the carrying capacity. We know what that is. That would have to be part of the initial value problem if you're going to be able to solve it for k. And we know that y sub 0 equals 1. So that would be the initial value problem. And that's that. And then last problem, number 41, is, again, they suggest the use of a graphing utility here, but I'm going to do it in a similar way to what we just did. So suppose that a residence hall houses 1,000 students. So what is 1,000 here? Think about that. The most students that could have the flu would be 1,000. So the carrying capacity is 1,000. Following the semester break, 20 students in the hall return with the flu. Hope you don't end up in a situation like this next year. So y sub 0, the initial value of students with the flu is 20. And 5 days later, we have 35 students with the flu. So we're going to use a logistic model to set up an initial value problem whose solution is the number of students who will have the flu t days after their return from break. So dy dt would be equal to ky times 1 minus y over the carrying capacity. And we know that y sub 0 is 20. That's the initial value problem. They want us to solve the initial value problem and use the given data to find the constant of proportionality. Okay, so I'm not going to do the crazy calculus separation of variables and partial fraction thing. I'm not going to do that with this here. Instead, I'm going to go back to this recipe for the solution here. So if you have that nearby to look at to see what I'm doing here. So I know that y is equal to, on the top I have the initial value, which is 20, times the carrying capacity, which is 1,000. So that would be 20,000 on the top, over the initial value, plus L minus y. L minus y would be 980, times e to the negative kt. And I don't know why I put that open parentheses there. Right? Now the problem here is, and they're pointing us toward it here, is they say use the given data to find the constant of proportionality. In other words, find k. Well, we do have another point here. We know that y of 5 is equal to 35. So I can plug that in and find the k. So it'll be the negative 5k, right? Plugging 5 in for t. And then we just have to do some algebra here. I'm going to swap sides here, so that'd be 20 plus 980 e to the negative 5k is equal to 20,000 divided by 35. I'm going to go ahead and do that. That's 571.429. I subtract 20 and divide by 980. So subtract 20, divide by 980. That gives me what? That's an awfully similar number, isn't it? So subtracting 20, oh, sorry. I see what I did there. So let's go back to this parentheses error, right? 571. Good idea to always pay attention to your answers and make sure they make sense, which that one didn't. Minus 20 and then divide by 980. That makes more sense. So that gives me 0.563 over there. And in fact, if I'm looking for correct answer to 3 decimal places, I should probably be keeping 4 here. Probably should have done that there. But is that a good example for you? And that's e to the negative 5k here. So natural log of both sides. I'll take the natural log of that, natural log of my answer, right, and then divide by negative 5. And that gives me k is equal to 0.115. So there's my constant. And I could rewrite this, this model now with the k in there if I wanted to. And then the last couple parts here, C and D, make a table that illustrates how the flu spreads day to day over the 2-week period. The best way to do that, if we have our calculator, is to go ahead and put in y equals, put in our model, which is 20,000 divided by, parentheses, 20 plus 980 times e to the negative 0.115 t, or that's going to show up as an x there. And then I'm going to go to the table, but I'm not going to go to the table yet. I'm going to go table set. I would like the table to start at, well, I guess 0 to see the, and then I'd like the table to go up by 1 for each day. And I want the table to generate automatically. I go to the table. And so you can see at time 0, these are our times, and this is how many kids have the flu. So 0, there's 20, and then on day 1 about 22 kids, and 25 kids, 23, and so on. There's 34.999, right? We knew at time 5 it was supposed to be 35. That's a nice confirmation that we did it right. And so on, and so on. And you can see that the rate is increasing slightly as we go from kid to kid, or day to day, rather. So there's the table. Did that with my calculator. And then D, they say use a graphing utility, but I don't think I really need to do that. I think I can just do this here. We're starting, the carrying capacity is way up here at 1,000. So if I do that'd be 500, that'd be 250. So we're way down here. And even by the time we got to day 14, we were only up to 92.64. So we're way down in the early stages of it. So that's what it would look like here. Eventually we would get to here, eventually we would come back down to where the carrying capacity, right? If you lock all these kids up in the same dormitory, they're all going to get the flu eventually. It's the moral of that story. Wash your hands.